Welcome to week 2 lecture 4. Now, in this lecture we will be talking about cryptanalysis and give a very simplified version of cryptanalysis of a block cipher, in fact rather to say a cryptanalysis of a single S box. But before that we have to understand what is meant by cryptanalysis. So, roughly speaking, cryptanalysis is the subject which is the interest of an attacker, because he would like to intercept messages sent by Alice to Bob, and without knowing the key he would like to know the key or at least the content of the message. Now, here there are several attack models depending on the power of the opponent or the adversary. So, the first model is ciphertext only attack. So, in this model the attacker has only access to ciphertext and nothing else. Ciphertext only attack. So, of course, we assume that the attacker knows the crypto system being used, he knows the circuits, he knows the algorithms and everything, but he does not know the particular key that is used by Alice to encrypt the message that he is encrypting. So, in this so the first model, as I said, the ciphertext only attack model, here we assume that the attacker knows only ciphertext and nothing else. So, it is a ciphertext only attack. Now, of course, one will say that what else do you think the attacker should be knowing? Now, the answer is that attacker in practice can know something much more, and that gives rise to known plaintext attack, where we assume that the attacker has several pairs of plaintext and ciphertext enciphered by using a particular key, but the attacker does not know the key. So, we come to known plaintext attack. So, here as I said, the plaintext ciphertext pairs x y's are available to the opponent. Well, then one can ask that how is it possible? The point is that in practice it is indeed possible, because it is quite possible that parts of the messages are something very standardized. So, everybody knows that if, let us say, Alice communicates to Bob, everybody may know that some parts of the messages that are being sent, it might be a form where many things that are written are common to everybody's form. So, one can know that when one can easily presume that, I mean, suppose Alice is talking to Bob, then one can assume that okay, we know that she must be sending this form. So, this part of the message is going to be this part of the form which we already know. So, I know the plaintext and ciphertext pair, but of course, I do not know the key. So, this is this model plaintext ciphertext known plaintext attack, and we would like definitely that our crypto system should be resistant to known plaintext attack. Now, there are certain other attacks which are also feasible, and we would like to have our crypto systems resistant to those attacks. So, one is chosen plaintext attack, where we have the attacker with the ability to choose the plaintext. Now, that is also something very strange. One would say that how is it possible, but it is not at all impossible, because for example, the Alice might be using a device to send message, but the device for some reason may be available to the attacker for certain amount of time, so that the attacker or Oscar can put chosen plaintext inside the device and check the ciphertext coming out of it and generate several pairs. This is possible. Now, the last one is chosen ciphertext attack, where the opponent can choose ciphertext and generate corresponding plaintext. Now, this is a scenario where the opponent has the access to decryption function. In our discussion, we will be particularly considering known plaintext attack, and chosen ciphertext attack, ciphertext only attack is difficult. So, we usually do not consider that, although it is possible in several instances to launch ciphertext only attack. So, we concentrate on known plaintext attack. Now, we go back to affine ciphers, which is a classical cipher, and we show that affine ciphers are particularly vulnerable to known plaintext attack. Now, affine ciphers are also vulnerable to ciphertext only attack, because when we encrypt plaintext to ciphertext by using an affine cipher, then the letters, each individual letter is mapped to a unique letter, and therefore, the statistical distribution is not changed. Therefore, we can see the statistical distribution and very quickly guess which letter is changed to which letter, and then we can kind of, since we know that affine cipher is used, so we might be able to know the key with less time than exhaustive search. But the known plaintext attack on affine cipher is even more serious. That let us look at this example. Suppose that we have two plaintext ciphertext pairs obtained from affine cipher. So, suppose this pair is 222 and 64, and now we ask a question, can we find out the keys, and suppose the key is assumed to be A B. We do not know the values of A B, but since we know that the plaintext 2 goes to 22, then we can write 2A plus modulo 26 B is equal to 22 and 6A modulo 26 B is equal to 4. So, we set up an equation. Now, let us look at this equation. 2A modulo 26 B equal to 22 and 6A addition modulo 26 B equal to 4. Now, what I can do is to multiply the first equation by 3, because after all 3 is not 0 mod 26. I can do that and still this relationship will hold, and we obtain an equation 6A plus 26 3B and equal to 66. So, we write these equations afresh. I have got 6A addition mod 26 3B is equal to 66, and of course, I have to put mod 26 here. I do not do that now, and here 6A plus mod 26 times b equal to 4. I could put mod 26 here as well. I do not have to do that because it is 4 already, and I am allowed to cancel 6a because if I subtract this this quantity from the top quantity, then also this relation, equivalence relation, is going to hold. So therefore, I will get 2 times b equal to 62 mod 26, and 62 mod 26 is going to be okay, let us see, I do not do anything right now. So what I do is that, okay, I see it is 62 mod 26. The question is, what does it mean? It is essentially is congruent to 62 mod 26. Therefore, I know 26 divides 2b minus 62, 2b minus 62, but 26 is 2 into 13. So, from this we know that 13 divides b minus 31, and by our definition b is an element of z sub 26, and the only such b possible is b equal to 18. So, I have retrieved b that I see over here somewhere, b is 18, and then I put the value of b in the first equation, so that I get 2a plus modulo 26 times 18, 2a plus mod 26 times 18 equal to 22, and which gives me 2a plus mod 26, no sorry. So, it basically gives me this, that 2a is congruent to 4 mod 26. So, 26 divides 2a minus 4, which implies 13 divides a minus 2, and I know that a is an element of z sub 26, and the only possible element is 15, and we see that we have retrieved a, and more so that a b is 15 18, and well, GCD of 15 comma 26 is 1. That means 15 18 is indeed a valid key of affine cipher. So, we have obtained a key by looking at just two plaintext ciphertext pair. So, I am giving you a very simplified example of a known plaintext attack on affine ciphers. Of course, affine cipher is weak, of course, affine cipher is a classical cipher, but it gives a very good example of this known plaintext attack. We see that it is weaker if we assume that the opponent has access to some, in fact just two plaintext ciphertext pairs. Now we come to something which is a very simplified block cipher. It is well, I think the most simplest possible block cipher, and of course it is not strong, but this cipher gives an understanding of what we mean by linear approximation attack. Now, so let us look at the description of this block cipher. Now, I will be eventually using an S box which is given by this. If you check that F1, by F1 I mean the leftmost column, this is F1, and by F2 I mean the second one. So, I have got the coordinate functions F1 F2, and the function itself, the S box is capital F, and I can write F1 F2 as arrays like this. Now, this is my block cipher, which is easy. I will draw a figure on the board as well. I have got 3-bit input and I have got the key mixing layer. I have got 3-bit keys. So, this is K1, K2 and K3, and inputs are X1, X2 and X3. That is what is happening here, and if you look here, I am doing the key mixing by bitwise XOR. So, after the key is mixed, this is this X XOR K, because my input is X and my K is key. It is a single round, single S box, no permutation layer S box. So, we are going like this. So, whatever is coming out is something like this: X3 XOR K3, then X2 XOR K2 and X1 XOR K1. It is coming like this, and then I am passing this through the S box denoted by F and whose function is given over there, and therefore, I am getting this. Oh no, I am getting only 2 output. So, just 2 outputs over here, and this output will be denoted by Y1 and this output will be denoted by Y2. I am not written over here, but please look at the blackboard, and Y1 is essentially F1, and then I will put those values. So, this is X3 XOR K3, comma X3 XOR K2, X2 XOR K2 and X1 XOR K1. This is F1, and Y2 is F2, which is F2 of X3 XOR K3, X2 XOR K2, X1 XOR K1. So, I have got this. Now, suppose I have got a plaintext ciphertext pair. So, that means that I have got this pair X comma Y. Then what I can do is that I can vary this K over all possible values, and there are 8 such values. So, because K is an element of GF2 to the power 3 and there are 8 bit patterns in GF2 to the power 3, I can vary this value and run this and see where the input is matching with output, and that is my candidate of key. This is called exhaustive search, and this is a very important technique, but our question is that based on the functional properties, can I reduce to something less than exhaustive search in this case? Now, here we see the weakness of this function is that if I add F1 and F2, then it becomes X2. So, F1 and F2 are essentially quadratic functions which are quite nice and all that, but if I add them, that is it is a component function. That component function is just X2. So, if I add Y1 and Y2, so let us see here, if I add Y1, let me write over here Y2 and Y1, then that means I am adding F2 X3 plus K3, X2 plus K2 and X1 plus K1 XOR F1 X3 plus K3, x2 plus k2 x1 plus k1, and I know that it is only x2, but in this case x2 is x2 XOR k2. So, this is what I am getting. Now, that means that I have got an equation involving k2. Let me write it over here. I have got an equation like this: k2 equal to x2 plus wait a moment. So, I have got this one, that means y2 plus y1 equal to x2 plus k2. Of course, this plus is XOR, and therefore, k2 is equal to x2 plus y2 plus y1, and this is interesting. Now, why this is interesting? Now, let me remove the calculations and just look at this particular expression. So, I remove this portion of the blackboard. Okay. I remove this, I do not want all these things, just the rudiments. Here k is coming in, and here this is y2 and y1, and this is, well, this is the input, this is the output, and I have got the access of a pair of input output variables. So, I know this. Knowing that means that I know x3, x2, x1 and y2, y1. I know particular values of this. Once I know this, I know that because of the properties of the function, k2 is equal to x2 plus y2 plus y1. I can always evaluate k2. Once I evaluate k2, that means that when I am searching over all the keys, one coordinate of the key is known to me, and that is k2. So, k3, k2, k1, this is the key string, this is known. Therefore, I have to search for only these two unknown keys, unknown key bits, and therefore, my search reduces from 2 to the power 3 to 2 square, because I have got just 4 possibilities. So, if I do that, I will be definitely able to get the value of the keys. So, this is what happens if a function, if a component function of an S box becomes linear. Now, one may say that okay, fine, it may not become linear, then what happens then? Now, in that case, even if it is close to linear, that is its Hamming distance is close to linear, then for if we take many pairs, probability that an equation like this, a linear equation, will be satisfied between some of the key bits unknown, which are unknown to the bits of the plaintext and ciphertext becomes high, and therefore, we can mount an attack which is, well, which will not be successful always, but some kind of statistical attack, and be very be quite positive, quite optimistic of getting a solution. So, this is a very simplified example of linear attack on a block cipher. Rather, I should say it is an example of a simplified example of a linear attack on an S box. Summing up, in this lecture we started off with the definition of cryptanalysis and the attack models. We saw that there are several attack models and we have to know which attack model we are using, and then we checked affine cipher and saw that it is not resistant to known plaintext attack, and finally we got a somewhat simplified idea of linear cryptanalysis. That is all for today. Thank you.